All right, welcome everyone. Excuse me for the technical difficulties. Welcome to the presentation Persistence Squared. And if this works. So my name is Juan Pedro. I'm the CTO of a music tech startup called Bronze. I'm also an independent consultant. I've been working for many years in the fields of music, graphics, films, robotics, real-time. And it's precisely because of this involvement in highly interactive and dynamic systems that I got very interested in persistent data structures. So what is a persistent data structure? When we hear the word persistent in the context of data structures, we have to forget our intuition that persistent means something like persistent storage, right? Like somewhere where you save information and that it resists rebooting the machine, right? When we talk about persistent data structures, we mean data structures where the values of the data structure persist after modification. This means that you can change the data structure, but whatever you had there before, whatever shape the data structure had before, is already is still there for you to access in some way. One way, and very common way to achieve this is through immutable data structure, right? We achieve this property in an almost tautological way, because if something is immutable, if a value is immutable, it persists, obviously, right? You cannot modify it. But some of you may be thinking, Juanpe, like, cut down on the microdosing or something like immutable data structures, like the whole point of a data structure is that it mutates, right? Like it changes. You put stuff in, you get stuff out. Hang on for a second. So I'm going to show you the library immer. So this is a library of immutable data structures that I've presented at CppCon already a few times before, actually. I think the first presentation was in 2017. And not to brag, but it's the default standard for immutable data structures in C++. For C++ developers. And actually, it's very production ready. It's used in production systems, even critical systems. At Meta, for example, we had a project where we really used it in super core infrastructure. I know it's used inside Google, Amazon. Recently, I learned in MongoDB, they use it in places as well. So it's very solid. It's very well tested. You're welcome to use it if you like what's presented here. So once we have an immer vector, we can declare a vector that is const, right? It's immutable, so we can mark it const. And we can call the pushback method of the vector, but since we cannot modify the previous vector, what we're going to get is a new version of the vector, right? So we had a vector A, and now we have a vector B. And because the value A persisted, we can do comparisons like say, hey, actually, before we had 3 items, now we have 4 items, right? And the 2 values are there for us to poke around. We can even do it again, right? So if we want to modify it, we cannot use the brackets because that cannot like return a new value the way you would expect. But we can use the set method and get a new vector with some value changed, right? How will we implement this? Well, if you're like a C++23 developer, you may try something like this, where you say the class immer vector contains an std vector inside, and we just write wrapper functions like this one, or wrapper methods. And here we're showing off one of the very nice and actually most wanted from me C++23 features, which is explicit this, right? So what we're doing here is saying that this argument of this function, we're explicitly declaring it as part of the argument list. And in this way, we can take it by value, right? Which is something that you could not do in C++20 even, right? There are other fancy things that you can do with this, like deducing the type and using universal reference here. We just want to get the vector by value so that, when I turn my head, can you still hear properly? I'm not sure, yeah? So that we can push back into the member vector. But this is a copy, right? That since we received by value that it's already inside this function logged in, and we can return a new version of our data, right? We can do this with the set method as well, and we're done, right? Mutable data structures, the talk is ready. But of course, you will think this wouldn't work in practice, right? The reason is that a standard vector stores all the data in a contiguous vector, so that whenever we need to change it in this way, right? If we make a copy of the vector, we're going to have to copy all the data, right? There's no way to say, just, I don't know, modify this little bit here without kind of referencing the rest. We will have to copy the whole data, right? So if we use this data structure a lot, you're going to get quadratic behaviors and like lots of copies everywhere. Your C++ developers, you probably are very aware of why you shouldn't do something like this. So we're going to need a different representation for our vectors. We're going to use something like this, a tree. And we're going to use a tree that is very regular. It's perfectly balanced, we call here. This is a radix balanced tree. I will talk a little bit more about it later. What's interesting is that all the blocks, all the data is stored in chunks that have a fixed size that is a power of 2. So here, for presentation purposes, I'm using blocks of 4 elements. In practice, we will actually use wider blocks. I'll talk about that later. Now, the nice thing is that since now we have smaller chunks of data that are related to each other, if we want to modify that vector v0 that we have represented in that tree, I don't need to copy all the data. I'm going to actually use this very regular structure to first address directly, without doing any search, the element that I want to address. Here it's like the index 9. So I can take, because I'm using 4 elements, the logarithm of 4 is 2, or in base 2. So we can group the bits that represent the index of the vector in groups of 2. And I'm going to use the first group of 2 to index in the root here, right? So we're saying we're moving through 0 here. Then we go through 2 here. And then here we have 2 as in C++ index 2, right, the third element. And here, the second element, j, right? So here's our j, and now we can copy that chunk. And of course, we're going to need a copy of the parents. But we didn't need to copy all the data, right? And this is how we managed to modify the data structure. Modify meaning create a new version, right? Create a changed version without changing the original one that shares a lot of structure. And this is the key word that you need to remember for this talk is structural sharing, right? This is the property of immutable data structures that make them work in a really nice way. And that give us really interesting properties, right? The fact that we have all these values that are actually, from the programmer's point of view, purely independent, right? They're value semantic, they're completely independent from the interface point of view, but under the hood, they share structure, right? And we achieve this through this tree structure, plus reference counting that you also need to be able to, track when this memory is deallocated or not. So this data structure, as I mentioned, is called the radix balance tree. And it's characterized by a branching factor m that is a power of 2. As I said, these blocks need to be very regular. In the slides, I was using a branching factor of 4. In practice, I use a branching factor of 32, right? So the constant b, which is actually what you normally use to define the data structure, is 5, right? And it is because of this that a lot of the operations in this data structure, we call them effective O1. And this is a little bit controversial. I heard some criticism in the past because of this. I didn't come up with this term. This term was actually invented by the person that made these data structures popular, which is Rich Hickey. Rich Hickey is the inventor of the language Clojure, and he made a very bold decision. It's the first programming language that decided to use this data structure as the default data structure to represent vectors in the language, right? So if you're using Clojure and you use a vector, you get in this data structure. And he argued that this is a good representation for a vector because in practice, random access in this structure is effective O1, right? If you know a little bit about algorithms, you will say, well, technically, it's logarithmic, right? It's logarithmic with this base, but the problem is, or the key thing is that the base of the logarithm is 32, right? What this means is that with just 5 steps in, you're already in like 40 million elements. You can, with 7 or 8 elements, you can address more elements than you can ever fit in any computer that we already have now or any computer that you probably can imagine in the next few decades. So if the maximum depth that you can go is like 7 or 8, in the really worst case, in the most common case, it's going to be 3, 4. Is that number a constant? Or is that number the result of your asymptotic O1? So anyway, you can forget about this effective O1 and say that it's logarithm, but I think it's an interesting idea to think about it in this way. The cool thing about this data structure also is that it's very cost efficient, right? Because we're storing data in contiguous chunks. These chunks are actually wider than cache lines. You can fit actually a few cache lines with one of these leaf nodes. So actually, when you iterate over this data structure in the right way, which I will show later, what's the right way, the iteration time is actually comparable to an STD vector, right? There's a very small difference. On top of that, the actual data structure that is implemented in immer is not the RRB, it's the relaxed RRB. And this gives us the property of logarithmic time, in this case, real logarithmic time, not effective O1 logarithmic, concatenation. And this is really cool because this opens the door for things that you cannot do with a standard vector, which is inserting in any position of the vector in logarithmic time. This opens the door also for all kinds of new parallel algorithms because, for example, if you want to do a parallel filter, right? Normally a parallel filter where you need to produce vectors of different size, right? So you cannot really like push in the same vector from different things without some kind of like locking algorithm. With this, you can just distribute the work. Each of the threads is gonna, produce their own filtered vectors on their subset of the work, and then you concatenate the results and get a new vector. This is quite interesting. Another interesting property is that growing this vector is not amortized O1, it's actual effective O1. And this is really nice because it means that you get a very stable latency, and for some use cases, this is actually a quite nice property. So yeah, this is a cool data structure that beyond the immutability aspect, it has also other interesting properties. Immer also has array map trees, and this is the equivalent. So we showed vectors, we showed a wide node immutable data structure for contiguous sequences. This is the equivalent for unordered maps, for unordered sets. And it's quite similar. I'm not going to go through all the differences. The important thing is that it's also characterized by a branching factor of 32. The tree is a little bit less regular because it depends on the prefixes of the hashes, but you also get very wide nodes with pretty decent cache locality. Actually, better cache locality than with a standard unordered map, because in a standard unordered map, you actually have a linked list on every element of the bucket. Again, this data structure doesn't require rehashing. So as you grow it and add new elements to it, you're never going to have, a stop big step, which means you get like a constant, or not constant, but like predictable latency on all operations. It's also very compact. Actually, in the project that I mentioned before with Meta, we were replacing some unordered maps that were synchronized with locks, and we were interested in the data structures because of the concurrency benefits that they give. But we actually saw afterwards that we got 50% decrease in memory usage because of moving to this data structure. So this is pretty cool. And the nice thing about this kind of data structure is that it opens the door for all kinds of new architectures. It's a kind of architecture that I like to call value semantics at scale, right? Because we often apply value semantics in little places here and there in our application, but it's difficult to kind of move the big values, the big documents, the big things in our application to pure value semantic. And value semantics at scale is characterized by, I would say, by three major advantages. The first one is concurrent programming. This one is the most obvious one, right? Let's say we have a document, and this document is using data structures of some sort. And if we're using mutable data structure, right, we're going to have one version of the document that everybody in our application is trying to access. The UI is like triggering actions that modify it. And at some point, you want to save it to disk. Well, if everybody's accessing this, and if we want to do this operation concurrently, we're going to have to use some kind of synchronization mechanism. In this case, I just put a mutex here, but this means that this operation is not actually concurrent fully, right? So if the saving to disk takes a while and the user tries to modify the thing, they're going to get a spinning wheel. It's not so nice. Plus, all the problems that mutexes have of they're a little bit of an error-prone technique. If you use immutable data structures, because immutable data structures share structure, copying an immutable data structure is as cheap as basically copying a pointer and maybe touching a reference count. You can just capture the whole document by value in your Lambda and save it to disk, and you don't need any synchronization, right? That's pretty neat, I would say. But another advantage of immutable data structures that I think is sometimes underappreciated is reasoning about change. What do I mean by this? In a lot of interactive systems, and the systems that I often work on, you have some kind of document, some kind of data model that the user manipulates, so you have actions that change it. And a thing that you need to do very often is to figure out what changed, right? So I did something to the document, what changed? And in this way, we can do updates in other systems. Like, for example, the UI needs to represent that change to the user, right? If you're making music software, like I often do, you need to represent that change in the audio graph or whatever is generating the sounds. So if you're using a mutable traditional system, well, you have the document, and the document is mutating all the time, but the previous values are not persisting. So if the previous values don't persist, you actually don't have information or not even a way to kind of recover that information about what changed. You change something, and that change is described in the code, but it's not described in the data that you have, right? And it is because of this that we resort to techniques like callbacks that as you go modifying things, right, the code is gonna explicitly say, well, I just changed this thing, right? I just changed the property foo of the document. Or I just changed the property bar of the document. And someone else is listening to this and trying to make sense of something like this, right? This means that when you change the document, actually you probably need some kind of helper function that hides the notification. But for me, one of the biggest problems with this technique, there are a few other problems, but the biggest problem is that it doesn't compose. So now if I have a complex operation that needs to manipulate multiple properties of the document at once, well, I can do set foo, set bar, and you will say, well, no problem. Well, the problem is that the user meaning like the clients of this API, are seeing all the intermediate updates, right? They may even see broken invariants. Let's say we have the invariant that foo has to be less than bar, right? We broke the invariant when we did that first set foo, right? And the UI may break or now have to consider the possibility that the invariant has to be looser. Basically, you have to loosen your invariants in some way. And as your application gets more and more complex, this leads to a lot of complexity. Wasted updates and often, like callback loops and the spaghetti code monster that takes over our code. When you're using immutable data structures, value semantics do compose, right? First, actually, I will argue that you don't even need to, well, here I'm not even using the immutable data structure, I'm using integers, right? But you don't even need often like this kind of accessor methods. You can just manipulate the value because you have your copy here inside the function, you took it by value. You can do whatever you want here, nobody's gonna see it. And then you produce a new value, and that's what other people may see, right? So from the point of view of the users of this function, this is like an atomic operation. It's like, it's not atomic in the concurrency sense, but it's atomic in the sense that nobody can see what's inside, right? And you can make other operations that are based on these complex operations, and you can grow your operations more and more complex, forming a tree where they compose, right? And nobody has a problem with what's made of what. And because things persist, you always have the previous value if you want, right? Which means that when you need to figure out, okay, what changed, you can just do a comparison, right? You can say, is foo different than in the previous value than in the last value? And one key thing here is that comparing vectors and comparing maps in immer, etc., is very cheap. Because if they didn't change, the pointer values internally of this tree data structure is going to be the same, right? Or if the shared structure, the equality operator is going to bypass all those parts that are shared. So this works very, very fast, right? And you may argue that it's not so nice to have to do these comparisons manually. There are other things you can do. There's another library, Lagger, that I've implemented. There are other talks about it where you have these things called cursors that do actually a lot of this comparing and diffing the tree for you. There are other cool things that you can do with the data structure, which is that this is not implemented for vectors, but it's actually implemented for maps, sets, and tables, which is another data structure that we have based on the hash arrays, which is when you have a map and you create a new map that has changed a little bit, you can actually use immer diff to give you the differences between the two values in a time that is proportional to the amount of change, right? If they have been derived from one another, right? So it leverages the structural sharing to be able to implement this in a very efficient way. So it can tell you, this thing was added, this thing was removed, and this thing was changed. So this is super useful. I use this all the time, particularly when writing software with UIs that uses immer in some way. And the other fancy thing that you can do with immutable data structures is time travel. What I mean here is, let's say you want to implement an undo history, right? All editing applications these days have that, even though we're losing that a little bit with mobile. But they used to have this, where you can always go back to the previous state of the document after you change something. And the canonical way to implement this, it's already in the Gango 4 document, is the command pattern, where the undo history has a collection of objects that they're called commands that actually implement the change that you want to do to the document. And they implement it twice. They implement it forward in a method perhaps called undo, and then backwards in a method called undo. And then you have all kinds of implementations for this for all your operations. This is nice in the sense that it gets the job done, but it has some disadvantages. One of them is that you have to implement the operation twice, and you have to make sure that undo is the inverse of do, which may be not so trivial to do in some cases, or open the doors for bugs. Another disadvantage is that you cannot jump between different places, right? So if I want to undo 30 steps, I have to undo them one by one, right? I cannot just jump to 30 steps ago, which, most of the time we just Control-Z or Control-Y, so you don't experience this, but, sometimes it will be nice to be able to just jump in time. Now, if you're using persistent data structures, your undo history can just be a collection of documents, right? That's it. Because of structural sharing, you're not going to waste a lot of memory by keeping all the copies of what happened before. Now, we get to a very sad moment because I had a very cool demo prepared here, but my computer didn't like the HDMI cable or something. So I'm just going to describe what was going to happen here. I know the demos are the best or the most memorable parts of my talks. I wanted to say, that the proof is in the pudding, right? So I wanted to show you a piece of software that is definitely not trivial, that uses all of what I'm talking about, right? It's not a toy software, it's actually software that we're making at Bronze. And in Bronze, we're making a system to make music that is non-linear and that is adaptive. This means that whenever you press play, you can get something slightly different. We don't do this with like crazy Gen AI stuff. We do this by allowing the artist in a piece of software called the Bronze Composer to create non-linear musical structures that have space for variation using probabilities in different levels of abstraction. And that's one side, the Bronze Composer software. The other side is we're making a new audio format and a very portable audio engine that you can integrate in different places, right? One of the use cases actually that we're really exploring now is video games, right? Which is very natural use case for this because you have music that goes on forever and that needs to kind of adapt to the environment. And this is all stuff that you can achieve with Bronze. And in Bronze, I have a screenshot here at least. When you open a Bronze piece, you can see this graph. This graph describes the structure of the music at a high level because it's composed of sections where each section has certain probability of going to another section or not, right? And these sections can be displayed in the upper part that you cannot even see the part of the screenshot here, but what I was saying is that in this upper part, you can load the sections and visualize them, play them back. You can even let the engine fill it up for you as you play the song. So it will load sections into this kind of workspace using the probabilities that are described in the section. No? So you can hear the music as the user will hear it, and you can visualize it here, and you can edit it in there. Right? And I was gonna do this fancy presentation where using this generative stuff, we could like make a song that is like hours long, and you can like select and move around thousands of regions and clips from sections to others, and you could take the undo history and hover over all the elements, and as you hover, that state is actually presented to you, and you can even hear it, right? So, and everything responds immediately, you know, zero latency anywhere, everything is super fast, which is pretty cool. But anyway, you have to take my word for it now. Now, this is really cool, right? But if we just stayed here, there will be no talk. There are some challenges that we need to face, right? Ominous music. We get to the part 2 of this talk, which is persisting persistence. Because what I described before, some of you may have seen already before. I've presented it in other talks about immutable data structures, but now we're gonna face the challenge of persisting persistence. And we're using now the term persisting here in a cheeky way in this double meaning, where we talk about persistent data structures, but we're also talking about persisting the data structures to disk. Now, for educational purposes, we're going to turn our beautiful radix balance trees into binary trees. And you can actually do this by yourself in the library by fixing the B factor that is given to you actually accessible as part of the template arguments. And this can be sometimes useful, you know, to optimize the data structure for your particular use case. We're going to set the B factors to 1, right? Which means that we have 2 to the 1 elements in each vector. And this will simplify the display of the things that we're going to show. Now, let's say we want to store our undo history to disk, right? Because I showed that very simple representation that works really well in memory. You know why, the structural sharing. But what happens when we want to save it to disk? A lot of software these days actually have this feature where you can, you know, load a session and you can still have the undo history that you had before. Another reason why you would want to do this is to have infinite undo, right? If you want infinite undo, at some point you may run off memory, so you want to continue saving your undo history to disk. Still not technically infinite, but maybe you will die before you can fill up your hard drive with undo steps. All right. So how will we do this? Let's try it first in the, let's say, intuitive way or the naive way. We have our document with and it's a very simple document here. It's just a document that contains a vector of strings. And we call this vector of strings data, right? So if we want to save this, we're going to use the serial library because it's convenient. I use it in many projects. And to serialize a struct with serial, you just have to define this method called serialize that can work both ways for saving and loading. What you're doing is basically describing how you iterate over your structure, right? It takes an archive as the first argument. It's templated because it can be a different thing depending on whether you're doing JSON or XML or binary. And you take your value and you call the archive with your data, right? And in this case, we use this MVP thing. It means a named value pair. So we give it a name. So if you're using a format like JSON or XML where you actually can see names in the format, this is the string that is going to use for that. Now, we also need to save the immer vectors, right? There is support for std array and std vector and all that stuff in serial, but there is no support for immer, so we can add it ourselves. And to do that, we tell it to serialize the size using this special size tag. This is what will make us get an actual array in JSON, for example, as opposed to an object. And then we iterate over every element. Sorry, this is for loading. We iterate over every element. So we loaded the size to know how many elements there are there. Then we iterate over every element. We load the element and we push it into the immer vector. There's something interesting here happening, which is that I'm moving the vector before calling pushback on it. And this will make this function work way faster than if you didn't have the move. Because here, we don't care to persist the intermediate values of m, right? And if we move it, immer does know that these intermediate values, they're not visible to anyone, and will actually do some of the mutations in place, and this will be way faster. In fact, filling up immer vectors using this pattern is similarly efficient to filling up STD vectors, with the difference that here you don't have sometimes like a big reallocation step, it's a bit more constant. There was a question there?
Where's the index I used inside?
The index I? The index I is the index, the number of the elements that I'm loading. So I load the size, so how many vectors, sorry, how many items that this array have, or this vector, and then I iterate that number of times. Yeah, yeah. When saving, I need to first save that size, right? With the same symmetrically, we use this size tag thingy. And then I use immer for each, and I just give the archive to the immer for each. This is also something noteworthy. Why is there immer for each when we already have STD for each in the standard? Is because immer for each does leverage, does iterate using internal iteration, I think it's the technical term. It goes inside the data structure, it doesn't use iterators, so it's more efficient, right? Because it traverses the tree directly without having to, if you use iterators, since it's a tree, you need to kind of store the stack of the of the thing in the iterator. It's not much slower. Often I just use a for loop just because I'm lazy, or I don't want the object size increase that this may introduce. But if you want to be super fast, use immer for each. So now for illustration purposes, we're going to create 3 immer vectors of strings. That's the data that we had in the documents, right? So if we go back, we had this document, the document was a vector of strings, right? Or contains that. So we're gonna create these 3 vectors. The first one contains 4 very simple strings. Then we add 2 new strings to the vector. And then we have a third state that is actually the same, right? Now the history is gonna be a vector of documents, right? So we put all of this into a vector, and we serialize this the serial way, which is you create the archive and you call the archive with your value, and we get this, right? So this value serial thing, it's like an artifact of serial because it doesn't know what's the name of that root object that you're giving it. There is a way to get rid of it. We don't need to go through that now. This works, it's nice, but there is a problem with this, right? The problem is that these values are independent. Let's think about it again. If we represent the 3 values that we had, they can be represented very compactly with this tree. So we had V1 that has 2 leaf nodes, right? Because it's a binary tree with 2 elements each. Then we had V2 that had 2 extra elements. So that's a root and does things to the leaf. Doesn't waste any space, no, it only does, allocates the new data that is necessary. We have V3 that is actually identical to V1, so, sorry, to V2. Instead, when we save, we get 3 completely independent vectors, right? Because serial doesn't know about the internal structure of immer. And this means that when we load, we're gonna get 3 different trees, right? We lost this beautiful structural sharing, and if we did this with a very long undo history, this is potentially going to blow up our memory use, right? This is not fun. Actually, the file already will be potentially really big, right? Because you will have all these like arrays with duplicate information, where A, B, C, D is listed 3 times in the JSON file, when in memory each letter appears only once. So this is not nice. Can we do better? Well, the way we're going to do better is by introducing the notion of a pool. Because the problem we have is that each vector is treated completely independently, right? Serial doesn't know about the fact that there are some vectors that share structures with others. So we are going to introduce this notion of a pool of vectors. Now, if we have a pool of vectors, maybe we can teach serial to look into what sharing happens between the vectors within the pool and actually serialize in some kind of JSON representation the actual internal structure of this pool. Then we can load the pool as a whole, and out of this pool, we can reconstruct the vectors with the shared structure that we wanted. This is pretty nice, and this is what this new library that I'm presenting today, that's called immer persist. It's in the immer distribution on master. It's a little bit experimental, so I will mention at the end some of the caveats, but it's usable, it works, and all the code that I'm presenting today, it's actually runnable code. So how can we use immer persist for our documents? The first thing that we're going to do is get rid of that serialized function, and we're going to replace it by boost HANA adapt struct. Now, if you're using C++ 26 reflection, of course, this is not needed. If you're on C++ 20, you can even use boost PRF to avoid this in some cases. I'm a little bit old school, so I use boost HANA. Maybe I could even use boost fusion adapt struct, actually. Michael and me were mentioning yesterday, we miss the old school template metaprogramming stuff. This morning, actually, I found out a very good explanation for why that's happening in our brains. If you're curious, ask about it in the questions. It's a little bit maybe too much. What HANA adapt struct does is that it informs boost HANA, which is a metaprogramming library that gives you compile time data structures, about the struct, right? So it tells it which are the members and all of this stuff. So then we can, at compile time, get this information and implement the serialized function, for example, in a generic way. So the serialize now doesn't have to be customized for a document. We can say for every boost HANA struct, to serialize it, you iterate over the members using HANA for each. You get the keys. These are kind of the identifiers of the members of the struct. And then you use this serial MVP getting what's on that key, right? Now, once we have this, we can go back to our previous example, right? So we have the vector of strings. We push those two new elements, and we have the third copy, right? So the data is exactly the same. We have the history that is exactly the same. But to save it, we're going to use serial save with pools, which is a function from immer persist that leverages serial to serialize all the data structures that happen in that document tree using pools. What's cool about it is that actually you don't even need to specify what the pools are. It will figure out what the pools are. It will combine all the vectors that have the same type. And then there is this policy thing, the boost HANA struct auto member name policy, which means use boost HANA precisely to figure out which pools there are in the thing. Give it some names automatically, and just get it working, right? So if we do this and serialize, now we get this beautiful, maybe not so beautiful JSON. It's definitely less human readable, but what's nice about this is that we do have the structural sharing in it. So if we look at the value 0 thing, value 0 is the actual history, right? The history, which is an array of three documents, right? And what you can see is that the vectors that are contained in the documents, they are not referenced directly, right? We don't see an array expanded there. It just gives it an ID. And you can already notice that the vector 2 and the vector 3, which are the same vector, they have the same ID, right? Then we have the pools. And the pools contain all the pools that are needed for our document. Now, since in our document we only had one data structure, that was called data. It already gave it the name data. This is sometimes convenient, sometimes it's a little bit confusing, because if you actually have vectors of the same type in different parts of your document, it picks up the name of the first attribute that uses this, this vector as the name, but you can customize this, don't get too hung up on this. It actually serializes the template parameters, right? Because it's not the same a vector with B1 than a vector with B2, and if you mess this up, the structure will be different. You could fuck up overloading, so this allows us to check, are we the right format when we're loading? Now we have the leaf nodes, and you can see in the leaf nodes, there's no duplication of information, right? We only have the 3 leaf nodes that we saw in our picture before. Then the vectors, there are only 2 vectors, right? Because V2 and V3 are the same, so there are only 2. And then there are 2 inner nodes. Now this is actually slightly different than what there was in the picture, because there is this tail thing here that watch the other immutable data structures talk if you want to know more about it, or I can explain in the questions if we have time. It's an optimization that the data structures have to change a little bit the shape of the tree. But for the most part, it's the same that we have in the picture, right? And this is nice. We now have structural sharing in disk. Here is a little overview of what happens in this policy thing. The policy thing is what does some of the magic that allowed it to be very automatic, but you can also do it manually. Depending on your application, you may want to do some of this. First, you say, what are the pool types, right? So this is like a Booz HANA collection, right? A compile time thing where you say, well, I want a pool for the vectors of strings, right? I want a pool for this and that. And maybe you want to skip some data structures that, because of the way they're used in your application, the structural sharing is not relevant. You can skip them there. Then you can give them names, and this is the name that you're going to see in the JSON, right? So we call them data there. We can call it something else. And then you can also customize the save and load for the root value, so you don't get that value 0 thing. You can give it a different name, like, for example, history. Okay, really nice. So we managed to get persisting to disk with this pool concept. Can we do something else that is kind of cool? Well, saving to disk is a transformation of the pool, right? You have a memory representation of the pool, and we transform it to a JSON representation. We could do any arbitrary transformation on these pools, right? And this is actually useful, and it solves this problem. Let's say you want to transform the strings of all these vectors that you have, right? So you can have a transform immer function like this that uses std transform and uses this trick of getting a transient. The transient just gives you a mutable API instead of having an immutable API that is compatible with standard library, right? Back inserter and stuff like that. So we transform the vector, we get new vectors using a function, right? So for example, we convert these 3 vectors that we had to uppercase. Now, if we do this, we have the same problem that we had with the serialization problem, right? The transform immer function doesn't see the internal structure of the vectors. It's going to iterate over every element of every vector and just, you know, very dumb and forward thinking, go and transform every item, and these things that were before interdependent in their representation suddenly become independent, right? And we waste memory. We also waste work because this transform function is actually transforming elements that it could have transformed only once, right? But using pools, we can apply a transformation over the pool and get a transformed pool where only the elements themselves have been applied this change, right? There is a very important use case for that in bronze, which is actually what I'm going to show here, which is how we deal with versioning of documents. There is no perfect way to deal with versioning, and all serialization libraries that try something else. Very often you end up like in your serialization code reading like a version string and doing one thing or another depending on what you do, of what version it was. I don't like that because it's kind of error prone. Like if you fuck up like in how you're actually interpreting the old version, you may not notice. What we do in Bronze is that actually for every version of the document, we just have C++ types that describe the schema in C++, right? Because we're using serial or Bushana for serializing them. And if we introduce a new version of the document, for example, instead of a vector of strings, it's going to be a vector of charts. We just copy-paste the things that change, we make the change, and then we have code that actually leverages Bushana to do most of the conversion automatically, so it traverses the tree, and only for the things that actually change, you need to kind of write your little conversion function that upgrades, right? And if you forget something, you're gonna get a compilation error, so there's kind of no way to kind of fuck up the versioning unless you modified an old version header, which you should never do, right? In a code review, it's very easy to see, hey, you modified the V1 header, why did you do that? No, you have to create a V2 header, copy paste, and do the change. So I like this, but this has that problem of like we are transforming between versions of the document, and we're kind of destroying the structural sharing if we use the naive approach. So how do we achieve this? To achieve this, we're going to write a transformation that applies, describes the transformations that we're going to do on all the pools of the document, actually. So for this, we have a Bushana map that contains entries for each type of data structure that I have in the document. Here, for the vector of strings, I'm going to convert them to I'm going to convert the values, right? Because that's the key thing here that we're doing, right? We're doing a transformation on the values of the vector, and that's why we can preserve the structural sharing. If you were doing something else, like a filter, you cannot preserve the structure, right? Because the structure will be different. But if you're just transforming the values, you can preserve the structure, and you describe the transformation in this way. Here we're doing a very stupid transformation that doesn't really make sense, but anyway, which is we're just getting the first element of the first character of the string. Right? We said, oh, we were using A, B, C, D. Why don't just represent it with the first character? If there was no character for safety, we just use a null character. Very stupid transformation, but highlights what we want to do. So yeah, that's the type of the vector. This is the transformation. You could have many of these, right, in a practical application where you have a complex document with lots of different pools. Now we have, again, the same example with our 3 vectors, our history that contains the 3 vectors. How do we transform this history? Well, first we're going to say, give me output pools. We distinguish between input and output pools. Output pools are pools that you can get values from, right? And we need to get the values out of it to transform them. So this is an output pool. Now we say transform the pool using the XForm, the transformation that I just gave you. With this, we get another pool, P1. And now we can transform the history itself, right? For the history, because there's no structural sharing, there is only one history, right? We're going to transform it using, in this case, standard ranges, just to be a little bit fancy. And what we have as an argument is a version 1 document, and we want to return a version 2 document. And we do that by converting the container using the 2 pools before. You actually need to pass the 2 pools because, well, the whole thing happens lazily, actually. So when you ask the transformed pool for a new pool, it's going to look up, in the previous pool if it's transformed or not transformed. And you pass it the container that you want to transform, and then you get the transformed container. So data here in the argument, right, it's the vector of strings. The data that you have in the variable is the vector of charts that you can return, and finally get the new history updated. And if I serialize to disk to just show the internal structure, you can see that it's basically identical to the other. Oh, sorry, I was waiting for one. You can see that it's identical to the previous document or the previous history. The only thing that's different is that the leaf nodes, they don't contain strings. Now they contain chars, and the chars are serialized as the code of the character. Right? So yeah, this is pretty cool, I think. And it gives us lots of things. There are more things I can talk about the library. I'm just going to go through them very briefly. I showed how to transform vectors. The hash tables and sets also work. You have to be a little bit careful though, because if you're saving to disk, you need to make sure that the hashing function that you're using is portable, right? You cannot just use std hash and get a different result on Windows or Mac, or even you upgrade the compiler and maybe you get a different result and then your documents stop loading. The hashing function has to be stable. Right? So we provide a wrapper for xxhash, which we found it to be kind of nice. You could use something else. You can convert also the key types. So if you have a map, you can actually convert the key type as long as the hash is the same, or as long as they are equivalent, actually. This is useful to have. We have it in our document because often, we have type-safe keys for tracks and regions and sections. And when we change versions, the key type actually changed, but the actual information that's underneath is equivalent. So it's an important feature to have, but you have to use it a bit careful. Anyway, when you try to convert something, by default, it's not going to let you do that. And then you have to tell it, like, please, I really want to convert this key type. It's safe. Also noteworthy, complex data models work. I mentioned already, if you have lots of data structures in your tree, all these functions, they're going to collect all the data structures and compile them up into pools per type, which is really nice. You can have as much sharing in the structure as you want in different parts of the tree. And one key thing that was actually very important for us is that recursive data models work. And this was actually quite tricky to get working, because you can imagine when you're loading something and it's recursive and the information is kind of in the pool, it's not that trivial at all. But this was important for us because we're working on a new feature where actually you were seeing like tracks with clips. We have this feature where you can actually have an arbitrary timeline in one of these clips that expands to other tracks with clips. And you can have more tracks with clips in any of these, and this can grow recursively, which is very expressive and pretty nice, but it was a little bit of a headache for this feature. But it's actually the original motivation that we had to implement immer persist, because we were not supporting persistent undo history, but we wanted to have that feature. And with that feature, it's very easy to kind of create a very complex clip in the timeline, right? And then you just duplicate it around to create loops and move it around. And all these duplicates, you want to preserve the structure, right? So this was very important for us. Finally, as I mentioned, the library works, but there are definitely some to-do items that we have. The first one is incremental processing, right? So at the moment, we save the collection in one step, or the pool in one step. For the undo history case, for example, it would be really nice to be able to save just the differences that have been introduced in the pool by this new document, right? So you save the undo steps as they come incrementally, right? And we have some ideas on how to implement this, but we haven't done it yet. I think binary formats are not working yet. It will be nice to get them working for some use cases where you want a more compact representation, which is also something that we can work on. It was quite worthy, the JSON that you saw before, right? It was, oh, you're sharing structure, but you actually have way more characters. We can actually make it more compact, but I thought, actually for the slides, it was nice to have some of the things spelled out. Serial independence, now we depend on the library serial. I think we don't fundamentally need to. It would be really nice to have some kind of hook where you can use your own serialization library. And build time, object size, when you have lots and lots of pools, particularly in our case where for every version of the document we have our own set of pools, build time and object size get pretty big. I think there are definitely ways we can improve on this, because part of the problem now, it's all templated, right? So for every pool, you get new serialization code for everything. But for example, the internal nodes of the data structure, they're the same regardless of what the type of your data structure is, right? So all of this could be kind of type erased, and using other techniques, I think we can definitely improve both on build time and object size. Also very important to thank Alex Chavalin. He actually did basically 99% of the implementation of what I presented today. Sadly, he couldn't come here to CppCon, so I showed it myself. Yeah, he's an excellent developer, has been working with Bronze. He's also an independent contractor. If you want to hire him for anything, I can definitely vouch for him. He's a really brilliant developer. Now, key takeaways. So, structural sharing, very important property of immutable data structures. They enable completely new architectures in our software. And with immer persist, you can leverage structural sharing across sessions of your application by storing it to disk. You can transform data structures and preserve the structural sharing. And I think this has value in a lots of applications. I think it was a key thing that we were missing to really be able to use this value semantics at scale, at really big scale. Also, I would say help us. So Bronze is a very small startup which sponsored most of the development of this immer persist stuff. But if you find this useful for your work, please hire Alex or any of us to continue improving on it. It's an ongoing progress. There are other companies that have contributed to immer in different ways. And it's beautiful that with open source we can all contribute a little bit, either financially or with code. If you guys want to try implementing some of the things that I've described or other things that you need for your own use case, please be my guest. A list of previous talks on this topic. I'm not going to go through them now because we're running out of time. I just want to say thank you all for listening. I'm going to leave it. Some people were taking pictures of it. Thank you all for listening. And if you have any questions, it's time to ask. Thank you. Yes.
Yeah, hello. Very nice talk. Thank you. I have two questions. So first, you mentioned that the pools are detected automatically, and no?
What is detected automatically?
The pools. The pool. I mean,
the pool, yeah.
What does involve that? I mean, it's like it's a costly operation to detect the pools.
Well, it happens at compile time. So that's why it uses BooShana. And since we had BooShana, then we could get rid of the serial code. We use BooShana to traverse your document, figure out all the types, and combine them into these types. So there's no runtime payment here. There's some payment on compile times, which depending on your document, it may be relevant or not. But
But let's say you have 3 immer vectors, like in your example. The library has to detect that they have shared information.
Oh, you mean that,
yes.
right?
Yes.
That happens, as you serialize. And
so there is a bookkeeping in the serialization.
Yeah, that's
that
part of
needed.
like the serialization. So, it's part of creating the pool that is then serialized.
It's not part of serial.
It's not part of serial,
Okay.
right? Exactly. It's part of immer or immer persist in particular. And as it goes, as it's kind of trying to serialize things, it finds the commonalities, etc. But there is no. It's kind of proportional to the amount of stuff that you're actually writing to this. So proportional to the amount of change that you have of the size of the actual final pool. So, so there's no like secret quadratic crazy thing in there. Yeah.
Second short question is, these immer vectors support iterators that like normal iterators that can be
you can iterate them normally. I showed the immer for each, which can give you a bit of extra performance boost where you need it, but you can also use normal iterators, and I use them all the time.
Is there any STD algorithm that you cannot use at all because it's so expensive, or all of them work?
There are algorithms that you cannot use at all because it's not even compatible. And that I don't recommend applying directly. For example, one key example is sorting, right? When you sort a vector, you need to actually go through the whole vector anyway, and you're producing a completely independent one, right? And you need to do a lot of random access. If you do this on an immer vector, you're probably you're gonna be kind of paying the price. So what I do in practice is I just copy it to a std vector, sort, and then convert to immer vector.
So the category that you gave to the iterator is not random access. You put something like forward.
It's random access, but it's not mutable. So that's why you cannot sort with it.
Oh, that's what prevents the sorting.
Right.
Okay, thank you.
Yeah.
Hi, thank you so much for the talk. And more than that, is like actually in our team we are like extensively using immer.
Oh,
it's like a big it's like a building block in a very large scale application. I get a question is like, so if like say we use in a composite way, like say immer of immer as a value type and all the way down. And if somehow the value type has to be a pointer, then what would be your recommendations? Like, say, how are you gonna deal with that?
You mean in the context of immer persist?
In the persist and the transition, if it's the value type is a pointer, right? So when we say get the value, if we want to get a value and try to make changes, we want to make a true value copy instead of a shallow copy with a pointer.
I'm not sure I'm fully understanding. Like if you're using immer, you're gonna have a vector of vectors, you're saying, for example,
yes.
right?
Yep.
Like from the point of view of your code, it's a vector of vectors. There's no pointer. Is the pools they're gonna actually
the value
find
the value itself, it's not like a vector of vector, but it's a vector of a pointer to a vector. Something like that.
Okay.
Yeah.
I see. And you wanna know how to translate these pointers that you're using.
Yes, so once we get, say, transition at that moment, we actually want to enforce true value copy.
I see. I guess, yeah, so you will need, if you're using this pool thing, right, you will need to translate those pointers, which is what the thing is doing under the hood, right? It's translating the pointers to those numbers and then getting them back. So I imagine there will be probably a way to do this. I don't have it now in the top of my head. I'm not sure it's actually, you can get it out of the API that we have now. But I think conceptually, it's something that could be added, right? Because that's part of what the thing is doing. It's translating.
Yeah, right now we have our own way to try to overload it, to get away with it. But I just want to see if you have any recommendations. Okay. What would be the best?
I'm not sure I'm fully understanding actually the problem. Maybe you can show me with code after and we can see if there is a better way.
Yeah, okay, cool.
Thanks.
Can I ask the last question?
Yes, please.
So I'm very interested in iterator categories in the context of the STL. So if you had all the power in the world to adapt the STL to your needs, do you think this involves like a new kind of intermediate category for iterators that you could exploit? Like for example, Q uses like segmented iterators, in a hack way.
Maybe, yeah. I haven't really thought of that. That could be a thing. I must admit that I haven't really prioritized STL compatibility. I was actually considering that we could have a V2 of immer that didn't use mutable APIs. Sorry, that didn't use immutable APIs by default. Because in the end, you can just have a mutable API, which is what the transient does, and use copy on write. That's actually the interesting thing is the actual structure that is underneath, and you can use copy on write and get exactly the same benefits.
Yes.
I'm using immutable APIs just because I was coming from the Clojure world, and it kind of encourages a way to think about things that it's a bit more value-y. So there are things that we can do in immer to bring you closer to the STL stuff. I could imagine that there are still things that you will need in the STL. Like, for example, if you're changing the vectors, okay, we're doing copy on write. You're not getting true references to things. It's a little bit of like a vector of wolf case, right? So maybe we will need to tweak some of the actual iterator categories. I'm not enough of like a STL lawyer to be able to tell you from the top of my head which changes you will need. But yeah, it will be, if someone wanted to have that will be an interesting problem to discuss. I mean, sometimes people ask me like, maybe this will be something nice to have in the standard, right? This type of container, actually, because I use this in all my projects now, actually. But I find the idea of like, making it make sense with the rest of the standard too daunting. So I haven't even tried. But if someone else wants to try also, they can maybe do this, right? But definitely what you're saying is what you will need to figure out as part of that work, how it makes sense with the rest of the STL and the iterator categories. Yeah.
Thank you so much.
Yeah, thank you. All right. So if there is no any other question, thank you very much, and see you around.